Hi, it's Terry Denery of the MathWorks. So I was showing this work to one of my colleagues the other day ago, the whole four bar going through a very simple movement, and was talking about how great feed forward control is. And so my colleague basically said to me, well, what's wrong with feedback? You know, PIDs have been doing the job real well for a long time. And I think it's a really very reasonable position. And so I decided, well, let's put together a demonstration on this and let's really kind of get into the details of it. And with regard to should you use purely PIDs and no feed forward, well, I think the answer depends. And it really depends on how good you need the system to be. And between you and whoever your customer is, that's where the determination of what good is. Okay, so anyways, I find it a very interesting topic, and so we'll kind of get into it. All right, so here's the model. I've removed my motor. Okay, and this is a point that maybe I'll hit even more strongly in another video, but the idea, why I wanted to get into the permanent magnet synchronous motor and field oriented control was to understand how good they could really be. And I think that the conclusion, as we've, at least I'll say, a reasonable conclusion as we've gone through our previous videos, is that field oriented control and permanent magnet synchronous motors are very good. And if you've properly selected your motor and you operate it, I'll say, let's say in the range of, I'll say torque and speed at which it's capable of, it can absolutely behave as I'll call it the ideal torque provider. Okay, so anyways, as components get really, really good, it kind of offers you this advantage in Simulink, which is that their behavior is so reliable that you don't even need to include them in your model. Okay, and so they'll offer you some simplicity and some speed. And so that's kind of what we're doing in this model. And so you might think of it also as we're just modeling the outer loop and that we're kind of using our mechanical controls to directly deliver the torque that will be delivered, to the linkage. All right. So anyways, let's look at this. And I kind of love kind of hitting this point that if I'm doing everything right, it's like my PIDs do nothing. All right. And we've seen as I do this that they're doing a little bit. And they're doing this very important part, which is dealing with the uncertainty, the unknown, the things that just cannot be anticipated properly by your feed forward controller. Okay. And in delivering, some attention to these kind of uncertainties, they make sure that your estimation is synchronized with what's really happening with the real system. Okay. And even in kind of the simulation world where we got tremendous control on what will be included in our representation of the system being controlled, even numerical error exists and it can lead to destabilizing things. It will essentially disrupt um, your intention as executed through the control. So anyways, let's get back to this view though. So in this one, feed forward's pretty much doing everything, feedback's doing nothing. All right. Now, if you look at this control, this little thread right there, that's my feed forward. If we looked in here, we'd see the MATLAB function with the direct solution to the equations of motion as provided by this tool, Motion Genesis, that I like so much. Okay, and so based on telling it the motion that we want, it tells us the ideal torque. All right, so what I want to do is take this little gain that I put in there and let's zero out the contribution of feed forward. All right, so we'll run the simulation again. Okay, and this time we're kind of seeing the blue do what the yellow did before. All right, and it looks like it did it almost exactly the same. All right, and by definition, the feed forward is doing nothing, so therefore the blue does have to do everything. And if we look at, well, actually, let's run the animation again. Sure looks very good. Okay, and as we look at um, the comparison of command with what's delivered, it's not exactly this statement I've been saying, which is the blue line's right on top of the yellow. You can see a little bit of the yellow right there. And more importantly, if you track the error, you'll see that we're operating at about 1 degree. I should have shown that graph before, so I need to show it to you right now. So that's in comparison to what we get with feed forward. Blue is on top of yellow, and that the error is on the order of 10 to the minus fifth. Okay, but 1 degree is really a very small angle, and it's uh, certainly reasonable to expect that 1 degree should be good enough. Okay, so anyways, in response to my friend and my colleague who said, well, what's wrong with doing it with all PID? I'd say that the answer is it depends. And it depends if you're good with 1 degree. All right. So, anyways, I think a couple things I want to go into with regard to this. And one is a kind of an ease of use thing. Now, from my perspective as a mechanical engineer and kind of knowing that I have something that can be very automated to create this feed forward, I'd say that I do have an ease of use. But what's probably more important to me is that I understand the fundamental basis of how this is really working, and I agree with it, and I have confidence that it, in general, will always work. Okay, but I do want to address ease of use, and I think there's a very good argument to be made that ease of use can be delivered quite well with PIDs. All right, and so I'm going to take you through the process of how that PID is set. So I just removed the one that we were using. All right, and so let's go into Simulink. Let's grab a new one, and we're going to essentially start from scratch here. All right, and we're going to work with the default values of what a PID is. You can kind of see essentially this little formula right here. I don't know if my mouse is clearly kind of bringing you to this in this image, but essentially the formulation shown right here, and that essentially there are the four parameters that are really good to define the functionality of what this PID is going to do. As you get into real implementations, you will make choices for discrete and you will make choices for sample rates. But just to keep things simple, let's keep it kind of in the continuous realm that is available through tools like Simulink. All right, so we'll go with those defaults. KP is 1, KI is 1, D is 0, and this filter coefficient used to calculate the derivative, we kind of see in that formula, that's going to be 100. But since D is 0, it doesn't matter anyways. So I think I'll run this from the animation this time. And so let's hit the little green button in the animation. This will be a new calculation. And so that's pretty interesting. And all it is, and I think if you've been somewhat involved in developing systems like this with controls, you're very familiar with the idea, well, that you need to choose the right values of KP, KI, KD, which will accommodate kind of the natural response of the system that we're working with, which is this 4-bar linkage and its reception of torque, right? And so one of the best features really, in my opinion, of Simulink, one of the things I've loved the most about Simulink is the tune button for the PID controller, right? And so as I'm clicking on this right now, you'll see it's essentially linearizing the system. Okay, so all this is based on linear control theory, and from linear analysis, you can get all kinds of great tools like Bode plots and root locus, and I'll say step responses, which can kind of facilitate um, the design of a really good controller, right? And so what we're looking at right now is the design of a very good controller. And so the automation of how this tool works has chosen some values for KP, KI, KD, and N that are going to give us some things that are really good. Rise time of 0.014 seconds is good. A settling time of a quarter of a second. Overshoot, it might not be super happy with 16% overshoot, but in general, we don't really see steps occur that often. And if they do, there's going to be some sort of overshoot. Anyways, I'm going to just kind of go with this. And so I'm going to update this control now. And certainly in the example we've put together, we've been very intentional in choosing a smooth transition. Okay, so anyways, let's go ahead and hit run again. And we'll run it from the scope this time. Okay, and because we are not giving it a step, but we are giving a smooth transition where we go from 0 to 90 degrees in a period of 1 second, we get a real good response. Okay, again, we saw this earlier. It's about 1 degree. All right, so anyways, you know, the 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 tools, that absolutely are delivered very nicely through Simulink, can make the tuning of a PID really pretty easy too. And and not everybody will agree with me on this point, but I'd say it's probably a wash. That I feel like I can automate the feed forward piece quite well, and I'm very comfortable doing it. And it happens very rapidly. In the same way, it's kind of automated the way that I'm going to get this PID response the way I want it. Okay. And so, as I said, we're not getting that 16% overshoot because we've been very intentional about choosing a transition that we know it can do quite well. All right. And that choice was really made for our feed forward piece. And so what I'd like to do now though is I would like to make it look a little bit more like a step response, but do it in a way where it's still physically possible in the real world. Okay. And all I'm saying there is really that step responses are impossible. That we're essentially requesting an instantaneous finite change in an angle for this linkage. Essentially we wanted to go from 0 to 90 degrees if it was a step in 0 time. It'd require infinite torque to do that, and of course that cannot be done. Okay, but we're going to choose something a lot more rapid, and so it'll look a little bit more like a step because we're requesting a transition to occur in a tenth of a second, right? And well, let's go ahead and run it with pure feedback this time. And so what we're going to see looks a lot more like a step with the more rapid transition. Um, Well, there's a few things of interest here. Is that we're beginning to see that overshoot that controls are kind of known for in responding to step functions. Okay, and so this time our maximum error is about 10 degrees where it was 1 degree before, right? So that might be a little bit more challenging to say that that's good enough. But maybe the short duration of it being that big is going to make it more palatable, and therefore maybe there is a judgment that says it's okay. Again, it depends on you and your customer and what you really define as good. Okay. Um, but what I do want to get into is let's put feedback back. I'm sorry, let's put feed forward back. Okay, so I'm going to essentially include this thread again by essentially multiplying it by 1. And again, we can see it can do it almost perfectly. This time we're operating at an error level on the order of 10 to the minus fourth. Okay. Um, so a couple things. All right. So here's where we're kind of monitoring the torque required. And we are now requiring, instead of zero point 0.3 Newton meters, almost 4 Newton meters at our peak. Might require a different motor to pull it off. But again, if we make the right choice, these things really do look like ideal torque generators. Okay, so I'm not concerned about such a thing. And again, whether or not it's done really is dependent upon what you need to do as an engineer and what your customer is asking you to do. Okay, so but what I want to really point out is that my intention can be accommodated, okay, and that there is no overshoot, okay. And to kind of finish this off, it's an amazing thing that the PIDs can respond to step functions, that they can be asked to do the impossible, and that they will deliver something. And quite often they deliver something that we all decide is reasonable, that it's good, and how do we decide if it's reasonable or good? It's because this is a very kind of mature, um, I'll say strategy, or maybe technology is probably the better word. But we have a way of defining good. That we have things like rise time, settling time, overshoot. We saw 16% overshoot. That we have ways of talking about the quality of behavior that's provided by the PID in response to this impossible request of a step change. Okay, and so PIDs really are pretty amazing that they can kind of handle this impossible thing. Okay, and I'd say that that's one of their strengths. Um, but I also say that that's in a way a little bit of its weakness. Okay, and here's where I want to come at this from a point of view, is that they allow you to be unintentional and they allow you to make impossible requests. You know, and and the problem with that is that how it gets from 0 to 90 is very much up to those choices for Kp, Ki, Kd, and even N, this thing that helps you calculate the derivative. And I'd say that automated tuning is a great thing, but I don't understand it, and I've worked at MathWorks 17 years. Yeah, and I kind of understand it. I understand it's based on an understanding of what they call the linear response, and there's some sort of optimization that's taking place to give you reasonably good overshoot, reasonably good rise time, reasonably good settling, and reasonably good, I'll call stability, as expressed through things like phase margin. Okay, but again, it's a very complex field, and we're all have benefited greatly from the great engineering that took place to really even figure out how to do this. And this was all done like 50 to 100 years ago. They figured out how to do this through like electric circuitry before these, digital embedded processors could even exist. So anyways, we're kind of inheriting, a technology that has served us quite well. But this idea that what could be not my first choice of what Kp, Ki, Kd are, but one that I'm relying on kind of existing formulas to optimize for me, is making that choice of transition. And I'm simply saying that you can make that choice yourself, okay? And make that choice in a good controller that can understand the mechanics itself, and from that, the not just the linear response of the system, but the full response of the system can give you a response that can be orders of magnitude better, right? Anyways, with regard to my colleague and my friend who made this suggestion, well, why not just do it all with PIDs? The answer is complicated, and I kind of like that because it allows us to really kind of um, get involved and make good choices to solve real problems. So anyways, I think that along this topic, I probably will proceed a little bit further with it, and I think probably at least two more videos. And one will be, let's get into the basics of PID. Certainly one of the issues with PID is you don't get anything unless there's error. These are error rejection systems that they will deliver zero torque if things are running smoothly and perfectly, right? So there has to be an error. And it is a dynamic system itself, but it's a dynamic system that is augmenting the dynamics of something physical, right? And because of that, there will be natural time constants. And so it's not just about error, but it's also about duration of time it takes to compensate or correct for the error. So we'll get into a video that kind of gets into PIDs from that perspective. But then I'll also get into the idea that we are working on a simple problem. It's a 1 degree of freedom problem, 4-bar linkage. It's complex in its own way because it is nonlinear mechanics and it is dealing with a gravitational torque depending upon the angle at which the 4-bar is set. And all I want to kind of get into is we get into more complex mechanisms. And as looking at a backhoe recently, and I'll probably bring up an image of a backhoe, but the main point I want to make here is it's what they call a multi-input, multi-output system. Okay, the other thing that's important about a backhoe is that there are, essentially joints of a mechanical linkage which are parallel to each other. And if they are parallel and they are kind of actuated, it's sort of like the actuation of a joint here will absolutely impact kind of the movement of a joint here too. And so as the mechanics gets a little more kind of real, but more complex, we'll see kind of additional shortcomings of PIDs. One is that the errors do accumulate. The error of this joint plus this affects essentially for a backhoe where the shovel will be. But there is also the fact that the mechanics itself um, is no longer independent for what's happening with each of those joints. And what that mechanics is can absolutely have a major impact on your ability to be successful in making those systems work. And so we'll see additional things that can motivate more interest in being more cognizant of what the mechanism is and express it through a good feed forward control algorithm. So anyways, thank you very much.